So thinking about that brings in the sort of question, what happens when you actually scale it? If all the materials were soluble in a single solution, then scale it would be fairly straightforward because reaction rates are constant. So the bigger you go, the same reaction rate as long as you've got the same concentration. And thermodynamics, the energies that's produced in the process, are predictable. But we need to think about the energy as well. It's not just solids, gases, and liquids. We've got to think about the thermodynamics in the system. So one example here where we take a 250 ml flask with 100 mils in it, and the reaction volume is 100 mils. The reaction surface area is 100 centimeters square, so the surface area is 1 per centimeter. If we do the same reaction, but now at 1,000 litres, the volume's 1,000,000 centimeters cubed, the reaction surface area is 50,000, and the surface area to volume has gone down by a factor of 20. So that means it's much harder to remove the heat in that reaction. So the heat transfer equals the surface area in the system times a constant, the heat transfer coefficient, times the difference between the internal and the external temperatures. So for chemical engineers, this is a very important equation that allows them to think about the energies that are being dissipated in a process. So thinking about gases, solids, and liquids again, if there's more than one phase, a gas, liquid, solid, then mass transfer effects will affect reaction rates, things like rates of dissolution, phase transfer, crystallization process, and so on. So I've got just a theoretical reaction here in which a reagent X, which is a solid, needs to dissolve in the solution. The rate of dissolution is affected by the mixing in the reaction. So the better we mix it, the more we can affect that rate of dissolution, the forward reaction, and we don't need to worry usually about the back reaction. We can also, in the reaction, add a reactant Y as a liquid, and that goes into the solution. But we often want to control the energies in a process. So in order to do that, we add things slowly so that we can remove the heat at the right rate, and we don't then overheat the reaction. But if we add it slowly, it means that it can only react with reagent X slowly as well. And if there's a catalyst in there, then the catalyst needs to combine with both of these materials, so the concentration of each of those components is important, and the concentration of the catalyst, which then gives the rate of the reaction. So the catalyst then, if it's a solid, is going to have to interact with solutions, and that will affect the forward reaction and even the back reaction if there is one. So then we go on to make a product that's in solution, but then it may crystallize out. So then we've got to think about what's the rate of that crystallization, how big, fast are those crystals growing, because that's going to affect the reaction as well, and if you scale up, those rates could well change. Similarly, if there's a byproduct that's a gas produced, the rate of the gas evolution is also going to not scale linearly because it depends on the surface area to volume in the system. So this simple reaction here, you could think about many bioprocesses or chemical processes that got things as complex as this or even more complex. And it shows you that you can't just do things bigger. You need to think about the chemistries and what's going on between the different rates and the different phases.